In 2017, the most effective models for language tasks were recurrent neural networks and long short-term memory networks. For years, these architectures were the standard for machine translation. These models processed information like a conveyor belt. To translate a sentence, the system had to read it one word at a time, calculating each step before it could move to the next. This created a significant bottleneck. When the path grows too long, the network struggles to connect the beginning of a sentence to the end. By the time it reaches the final word, the mathematical representation of the first word has often faded. This sequential nature also meant you couldn't calculate step 10 until step 9 was finished. Because the work couldn't be split up, it created a massive computational traffic jam that made training on large datasets incredibly slow. The long-standing rule of processing language chronologically had become a ceiling, limiting how much these models could learn and how fast they could grow. But what if we abandoned the conveyor belt entirely and looked at the entire dataset at the same time? That was the radical proposal in the paper Attention is All You Need. It introduced a new architecture that functioned differently than anything before it, the transformer. By discarding recurrence and convolutions in favor of pure attention, the researchers enabled massive parallelization, allowing the architecture to finally take full advantage of modern hardware. To see how it works, look at this sentence. The law will never be perfect, but its application should be just. Instead of reading this from left to right, the transformer processes every word in this block at the exact same moment. It uses a mechanism called self-attention. This allows every word in the sentence to instantly calculate its relationship to every other word, regardless of how far apart they are. Each word is assigned 3 vectors: a query, which is what the word is looking for, a key, which is what the word contains, and a value, which represents the word's actual meaning. When the model encounters the word "it's," the query for that word scans the keys of every other word in the sentence. It matches with the key for law, creating a strong mathematical bond that tells the model exactly what "it's" is referring to. This instant matching allows the machine to resolve context and pronouns immediately, without needing to process the text in order. The model doesn't just do this once. As seen in this diagram, it projects these vectors across 8 parallel attention heads that all run at the same time. In this visualization, you can see one specific head handling an afro resolution, linking "it's" to law and application. Simultaneously, these other heads are mapping the structural grammar and the broader syntax of the entire sentence, capturing different layers of meaning at once. All of these different perspectives are then combined and passed through the 6 layers of the encoder and decoder shown here. This multi-head approach allows the machine to hold multiple contextual interpretations of a sentence in its memory at the same time. But if the model sees everything at once, how does it know which word came first? Without a sequence, "the dog bit the man" looks identical to "the man bit the dog." The solution is a technique called positional encoding. The model injects sine and cosine waves of different frequencies into the data. These waves create a unique mathematical signature for every position in the sentence. This signature acts as a timestamp, giving the machine the benefits of word order without the slow one-by-one processing of the old bottleneck. The performance gains were undeniable. The transformer set a new record in English to German translation, achieving a score of 28.4 and outperforming systems that had been in development for years. It also required far less time and money to train. The big model reached these results in just 3.5 days, using the 8 GPUs seen in these racks. The real success was in the math. By reducing the work needed to connect distant words to a constant, fixed operation, the researchers solved the long-range dependency problem that had plagued AI for decades. By proving that attention alone was sufficient, this blueprint moved past the constraints of sequence modeling, providing the mathematical framework for the generative AI systems that followed.